The universe is a vast and mysterious place, an endless expanse that stretches beyond our wildest imaginations. It is filled with billions of galaxies, each containing billions of stars, planets, and other celestial bodies, all bound together by the force of gravity. We have learned so much about the cosmos, from the smallest particles that make up matter to the largest structures that span across light years. Our journey of discovery has taken us from the quantum realm to the vastness of intergalactic space. Yet one question continues to intrigue us: how will it all end? This question has puzzled scientists, philosophers, and dreamers alike for centuries. The fate of the universe is a topic of great scientific inquiry, sparking our imaginations and challenging our understanding of the cosmos. Will the universe meet a cold, dark end, or will it face a fiery, cataclysmic demise? Will the universe continue to expand forever, its energy dissipating into an eternal night, where stars burn out and galaxies drift apart, leaving a cold, dark, and empty cosmos? Or will it one day collapse upon itself, returning to a state of infinite density, a scenario known as the Big Crunch, where all matter and energy are compressed into a singular point? Perhaps an even more dramatic fate awaits, a cataclysmic event that tears apart the very fabric of space-time, an event so powerful that it could reshape the universe in ways we cannot yet comprehend. These are not mere science fiction scenarios, but possibilities grounded in our current understanding of physics and cosmology. As we continue to explore and learn, we inch closer to uncovering the ultimate fate of the universe, a cosmic question mark that drives our quest for knowledge and understanding. Before we delve into the potential endings, let's consider what we know about the universe's current state. The cosmos, as we observe it today, is a vast and dynamic entity, filled with countless galaxies, stars, and other celestial bodies. We know that the universe is expanding. This expansion is not just a simple movement, but a profound transformation that has been occurring since the Big Bang, over 13.8 billion years ago. This means that the space between galaxies is constantly growing, like the dough of a raisin bread rising in the oven. As the dough expands, the raisins move further apart, just as galaxies do in our universe. The observation of distant galaxies rushing away from us, their light stretched and redshifted, provides compelling evidence for this expansion. This redshift is akin to the Doppler effect, where the wavelength of light elongates as objects move away. But what drives this expansion? Scientists have long pondered this question, and the answer is both fascinating and complex. And what does it mean for the universe's ultimate fate? Will it continue to expand forever, or will it eventually slow down and collapse back on itself? The answers lie in the interplay of gravity, the force that pulls matter together, and a mysterious force called dark energy, which seems to be pushing everything apart. Dark energy, which makes up about 68% of the universe, is the key to understanding the future of our cosmos. Its nature and properties remain one of the biggest mysteries in modern astrophysics. One possible ending, often called the Big Freeze or the heat death, paints a picture of a universe that continues to expand indefinitely. In this scenario, dark energy wins the cosmic tug-of-war against gravity. The expansion continues to accelerate, pushing galaxies farther and farther apart at an ever-increasing rate. As the universe expands and cools, stars will slowly exhaust their nuclear fuel and fade away. New stars will form less and less frequently, until eventually the universe will be populated by only dim remnants of stellar corpses, white dwarfs, neutron stars, and black holes. To understand the Big Freeze, we must grasp the concept of dark energy. This enigmatic force constitutes roughly 70% of the universe's total energy density and acts as a sort of anti-gravity, pushing everything apart. While we don't fully understand its nature, its presence is inferred from the observed accelerated expansion of the universe. In the Big Freeze scenario, dark energy maintains its dominance, ensuring that the expansion continues without end. As space expands, the matter within it becomes increasingly diluted. Temperatures plummet as energy spreads out, approaching absolute zero. Section 5. The Fate of Stars, From Brilliant to Black. The Big Freeze paints a rather bleak picture for the future of stars. As the universe ages and expands, the gas clouds that give birth to stars will become increasingly diffuse. Star formation will dwindle, and the brilliant furnaces that illuminate the cosmos will slowly extinguish. Existing stars will exhaust their nuclear fuel. Sun-like stars will swell into red giants before shedding their outer layers, leaving behind white dwarfs. Massive stars will go out with a bang, exploding as supernovae and leaving behind neutron stars or black holes. Section 6. The Big Crunch, a universe in reverse. The Big Crunch offers a dramatically different fate for the universe. Instead of expanding forever, this scenario proposes that the universe's expansion will eventually slow down, halt, and reverse. Gravity will ultimately triumph, pulling everything back together in a colossal cosmic collapse. Imagine the expansion of the universe as a ball thrown upwards. Initially, the ball ascends with great speed. However, gravity gradually slows it down until it momentarily stops at its highest point. Then it starts to fall back down, gaining speed as it goes. Section 7. Gravity's Pull, reversing the expansion. In the Big Crunch scenario, gravity acts like the unseen hand that pulls the ball back down. The combined gravitational attraction of all matter and dark matter in the universe eventually overcomes the outward push of dark energy. The expansion first slows down, then halts altogether. Once the expansion reverses, the universe begins to contract. Galaxies draw closer together, their light blue shifted as they rush towards us. The universe shrinks, becoming denser and hotter as it collapses upon itself. Section 8. Back to the beginning, the singularity. The concept of the singularity is one of the most fascinating and mysterious aspects of cosmology. As the Big Crunch progresses, the universe becomes increasingly chaotic and extreme. Galaxies collide, stars are torn apart, and the very fabric of space-time begins to warp and twist under the immense gravitational forces. Temperatures soar as the cosmos compresses, mirroring the conditions of the universe's earliest moments. The heat and pressure become so intense that atoms are stripped of their electrons, creating a superheated plasma that fills the universe. Stars are ripped apart, and matter is squeezed together with unimaginable force. Neutron stars collide, releasing bursts of energy that ripple through the cosmos, adding to the chaos. Ultimately, everything in the universe converges on a single point, a singularity of infinite density and temperature. This point is so dense that not even light can escape its gravitational pull, creating a black hole of unimaginable proportions. This singularity marks the end of the universe as we know it, but it could also represent a new beginning. Some scientists believe that the singularity could be a gateway to another universe, or even a new cycle of creation and destruction. Some theories propose that the Big Crunch could trigger another Big Bang, giving rise to a new universe from the ashes of the old. This cyclical model suggests that the universe is in a constant state of birth, death, and rebirth, an eternal cycle of creation and destruction that has no beginning and no end. Section 9. The Big Rip, a universe torn apart. The Big Rip presents the most cataclysmic end-of-universe scenario. In this scenario, dark energy doesn't just drive the expansion of the universe, it becomes increasingly powerful over time, eventually overwhelming all other forces, including gravity. Imagine a fabric stretched taut. In the Big Rip scenario, dark energy acts like a force constantly pulling on this fabric, stretching it further and further until it eventually rips apart. The key to the Big Rip lies in the nature of dark energy. If dark energy's density increases over time, it could eventually become so powerful that it overcomes the fundamental forces holding everything together. This means that not only will the universe continue to expand, but the expansion will accelerate at an ever-increasing rate. This relentless expansion would have catastrophic consequences. Galaxies would be torn apart, stars would be ripped from their orbits, and even planets would be shredded. Eventually, the very fabric of space-time would be ripped apart on a subatomic scale. Section 11. A Cosmic Mystery. Pondering the possibilities. These three scenarios, the Big Freeze, the Big Crunch, and the Big Rip, offer a glimpse into the possible fates of our universe. Which one will come to pass? The answer remains a mystery, contingent upon the properties of dark energy and the universe's ultimate fate. The universe, in its vastness and complexity, continues to challenge our understanding. While we may never know for certain how it all ends, the pursuit of these answers drives us to explore the cosmos, unraveling its secrets and contemplating our place within this grand cosmic drama.